Hello everyone. Hello everyone. Today we are going to study some different type of examples of the chapter, that is direct and bending stresses. Yesterday we have seen some basics examples, so today we are going to do some advanced level of examples. So let's start. So the first example is a masonry pier that is supporting a vertical load of 60 kilonewton as shown in figure. Then we have to compute the stresses at each corner of this pier. There are basically the four corners A, B, C and D. We have to find the stresses at these four corners of this column. The load P is acting at an eccentricity. એક્ઝામ્પલમાં ઇસેન્ટ્રિસિટી એ એક્સના રિસ્પેક્ટમાં એઝ વેલ એઝ વાયના રિસ્પેક્ટમાં આપણને આપેલી છે. ઓકે, સો લેટ્સ here the cross section dimensions of the column is given, B equal to 5 meter and D equal to 4 meter, and the load is given to us, that is 60 kilonewton. So first we will compute the area. So the area will be a B cross D, so it is 20 meter square. Next, from area and load we can directly easily compute this direct stress, that is load upon area. So load is 60 kilonewton and area is 20 meter square, so it's coming 3 kilonewton per meter square. Now next we have to compute the bending stresses. Bending stress will be equal to M by Z, but here the M will be the different in different direction. For X direction M is different and for Y direction also M is different. So for X direction M will be equal to Mx will be equal to load into eccentricity. Here the load is 60 kilonewton and for the this X direction eccentricity is what, 1.25. So the load so along this X direction bending moment will be equal to 75 kilonewton into meter. Same way bending moment along Y direction, so Y direction થી eccentricity 1.5 meter છે, so એટલા માટે જે છે bending moment about this YY axis will becomes 16 to 1.5, that is 90 kilonewton into meter. Now same way we have to find out the section modulus along this XX axis also, along the YY axis also. Yes, we have already seen the equation, how to derive this equation for section modulus along the different axes in the previous session. So by using that equation we can easily find out this ZXX and this ZYY, and from this ZXX and ZYY we can compute the bending stresses along X direction as well as along the Y direction. Now we have to compute from this bending stresses along X direction, bending stresses along Y direction and the direct stress. We have to compute the stresses at the corners. For that purpose let's see one sign convention system first. So it is a basic figure. The load we are considering at a point A. So for the sigma x, on the sides of loads we have to consider the tension and on opposite sides we have to consider the compression. So here the point A, here the load is A. So for A we are calculating the combined stresses. Then along the sides of load we have to consider the tension, so it is negative, and on opposite sides of tension we have to consider the compression, so it is positive. Same way for the sigma y, on the sides of load we have to consider the tension, so it is negative, and on opposite sides of load, so on this side we have to consider the compression, that is positive. By using this sign convention system we can find the stresses at corners. So for the A, for point A, direct stress plus bending stress in x direction minus bending stress in y direction. So for this A, the load is on that side, so we are considering the tension on that side. So here the tension is considered positive, then we have to consider the compression as negative. So for sigma x, the tension is positive, and for the sigma y, load is on opposite sides. Load will be on this side and our point of consideration is on left side of that. So we have to consider the opposite side, or we have to consider the compression over that, and compression here in this example considered negative, so we have to put the negative sign over there. So for this point A, direct stress is positive, bending in x direction is tension positive, bending in y direction compression negative. Same way for the point B we can find out. So for this point B, see, in x direction as well as in y direction, both sides there will be the tension, because it is coming on both side. બંને બાજુથી એ લોડની ડાયરેક્શનમાં જ છે, સો બંને બાજુ પોઝિટિવ આવશે. સો ઇન ધીસ કેસ both will be in tension. So sigma x direction positive, sigma y direction also positive. For the C, point C, so for C, sigma x will be the under compression and the sigma y will be under tension. So sigma x will be negative and sigma y will be a positive. Sigma x will be negative and sigma y will be positive. Okay. Now for the point D, so for point D, sigma x will be also in compression, sigma y will be also in compression, so both should be a negative. So for the D point, both should be a negative. Okay. So based on this, we can easily compute the bending stresses at each corner point of this column, and we can simply represent it on this diagram. Now let's another example, that is a cross section of concrete pier is shown in figure. It is subjected to the 5 compressive load. P1 that will be equal to 150 kilonewton, P2 that will be equal to 100 kilonewton, and P3 that will be a 200 kilonewton, and P4 that is 250 kilonewton, and P5 that is 100 kilonewton. Now these load are acting at this P1, P2, P3 and P4 point. We have to find the stresses at each corner point A, B, C, D and O. Okay, so let's start. So here the total load will be what? So P1 that is 150, P2 that is 100, P3 that is 200, P4 that is 250 and P5 that is 100. So total load coming is 800 kilonewton, and the area of section that is given to us is 3 meter by 2 meter, so area will become 6 meter square. So by using these two, total load and by using the area, we can easily find out the stresses, that is direct stress. So direct stress will be equal to load upon area. So load is 800 kilonewton, area is 6 meter square. So by using that thing, we can easily find out the direct stress, that is 133.3 kilonewton per meter square. Okay. Now we are finding out the moment of inertia about both the axes, x axis as well as y axis. So these are the equations, and based on that, so moment of inertia about x axis, that is 3 into 2 cube divided by 12, and about y axis 2 into 3 cube divided by 12. So by using that, we can find out the moment of inertia about both the axes easily. Okay. So next, from this next step is we have to find out the moment about both the axes. So there are 5 loads, then we have to take the moments of each load about the axis. x-axis as well as y-axis. So here the calculation of moment is there, and the moment in x direction that's coming as 0, that means there is a no bending moment about the x-axis. So by using this moment and the section modulus, we can easily compute the bending stresses, that is m y by I, or we can say m by z. So we can easily compute the bending stresses, and from this direct stress and bending stress, by using a sign convention system that already we have previously seen, we can compute the stresses at each corners of the section. Okay, so now in this chapter we have left one topic, that is hollow rectangular section. So now we will see that how to compute this section modulus for this hollow rectangular section. Here consider this hollow rectangular section having a outer width, outer dimension as a capital B and capital D, and inner dimension as a small b and small d. So the moment of inertia about x-axis will becomes what? So capital B into capital D cube divided by 12 minus small b into small d cube divided by 12, and y max will becomes only capital D by 2. This is the important thing that you have to keep in your mind. In this case, y max will becomes only capital D by 2. So same way we can take about the y axis. So it will becomes a Iyy divided by y max will be becomes a b by 2. So already we have seen in previous lecture that to get the conditions we have to use the equations for this minimum eccentricity, that is E should be less or equal to z by a. So we have to put the equations of z and area, that will becomes b capital BD minus small bd. So by putting that, we will get the equations or conditions for the eccentricity in x direction as well as eccentricity in y direction. Okay, so same way we can do this thing for the circular section also. So for circular section having the outer diameter capital D and inner diameter as a small d, we can find the section modulus, we can find out the area, and by using that we can do the E minimum should be less or equal to z by a. So by putting that in this equation, we will get the answer as a solution. So condition, so d raised to 4 minus d raised to 4 divided by d, and divided by area, that is pi by 4 d square minus d square. So 32 by 4, that will becomes 8, and d denominator ma avse, so d into d square minus d square. Now in numerator, that is d raised to 4 minus d raised to 4, we can write it as a d square minus d square into d square plus d square. It's look like that. A raised to 4 minus b raised to 4, that will be equal to a square minus b square into a square plus b square, or we can say a square minus b square will be equal to a minus b into a plus b. By using that formula, we can convert it, and we will get our final condition as capital D square plus small d square divided by 8 into capital D. So the load must be applied within this limit so that there will be the no tension anywhere in the section. Now based on this hollow circular section, we will take one example, that is a short cast iron column of the hollow circular section that has a projecting bracket that carrying a load of 1150 kilonewton as shown in figure. The load line is of the axis of the column by 330 mm. The external diameter is given to us 330 mm and the thickness is given to us 30 mm. We have to find the maximum and minimum stresses. So the load is given to us 1150 kilonewton. So 1150 into 10⁻³ ન્યૂટન થઈ જશે. ઇસેન્ટ્રિસિટી આપેલી છે 330 mm એન્ડ આઉટર ડાયામીટર 330 છે, થિકનેસ 30 છે. સો ઇનર ડાયામીટર શું થઈ જશે 330 માઇનસ 30 એટલે ઇનર ડાયામીટર આપણે અહીંયા થઈ જશે 300. સો એરિયા આપણે ઇઝીલી ફાઇન્ડ આઉટ કરી શકીએ છીએ π/4 કેપિટલ ડી સ્ક્વેર માઇનસ સ્મોલ ડી સ્ક્વેર પરથી. સો એરિયા મળી જશે, લોડ આપણને આપેલો છે. સો લોડ અને એરિયા ઉપરથી આપણે જે છે ડાયરેક્ટ સ્ટ્રેસીસ ઇઝીલી અહીંયાથી ફાઇન્ડ આઉટ કરી શકીએ છીએ લોડ અપન એરિયા પરથી. સો લોડ અપન એરિયા ઉપરથી આપણે ડાયરેક્ટ સ્ટ્રેસીસ ફાઇન્ડ આઉટ કરી લઈશું. નાવ આપણને ઇસેન્ટ્રિસિટી આપેલી છે, લોડ આપેલો છે, સો બેન્ડિંગ મોમેન્ટ મળી જશે. સેક્શન મોડ્યુલસનું ઇક્વેશન્સ પુટ આઉટ કરીશું. π/32 d⁻4 - d⁻4 ડિવાઇડ બાય કેપિટલ D. સો બાય યુઝિંગ ધેટ સેક્શન મોડ્યુલસ ફાઇન્ડ આઉટ થઈ જાય. By using this section modulus as well as bending moment, we can find out the bending stresses. Bending stresses M/Z. You have to put the data, and by using this, we can compute the direct plus or minus bending stress. Plus will give us some maximum bending stresses, and minus will give us a minimum bending stresses. So by using that, we can easily find out the positive and negative. સો મેક્સિમમ એઝ વેલ એઝ મિનિમમ બેન્ડિંગ સ્ટ્રેસીસ મળશે. અહીંયા મિનિમમ બેન્ડિંગ સ્ટ્રેસ નેગેટિવ આવે છે. ઇટ શોઝ દેટ ધેર વિલ બી ધ ટેન્શન ઇન ધ સેક્શન. So let's quickly revise what we have seen today. We have seen some advanced level of example of this direct and bending stress. One example having a eccentricity in both the direction. In that case, we have to compute the bending stress in both the direction, and we have to calculate the stresses at each of the corner. We have seen one important sign conventions for it. By using this sign convention, you can solve so many examples, and also we have seen there are so many loads on the one column. So how to find out the stresses at each corners, that we have seen. Then we have seen the hollow rectangular section and hollow circular section, and based on this hollow rectangular and circular section, we have seen one example how to solve this hollow circular section.